I'm Lawrence Krauss, and welcome to the Origins Podcast. On the last podcast that we aired, Andy Knoll and I discussed the first 4 billion years of life on Earth, addressing questions of how life affected the Earth, the geology of the Earth, and vice versa. Clearly important questions to try and understand the origin of life and its interaction with our planet, which address the more foundational question, perhaps, of is it possible that life originated not just here on Earth, but elsewhere, either elsewhere in our solar system, on other planets, or maybe moons of planets? Equally important, what's the likelihood that life developed elsewhere in the universe, on extrasolar planets around distant stars? Clearly, one of the prime developments that have affected that whole search was the discovery of extrasolar planets. The first extrasolar planet was discovered by Michel and Didier Queloz, and then immediately followed up by the discovery of other extrasolar planets by Geoff Marcy and his team, who discovered 70 of the first 100 extrasolar planets, including the first extrasolar planet located more than 5 AU from its star, about the distance of our current gas giant planets in our solar system. And equally important, the discovery of the first planet that transited its star and dimmed the light of its star. Now, the two techniques that have been used to discover extrasolar planets, looking at the Doppler shift as the star moves in response to the motion of planets around it, and this transiting technique, were spearheaded by Marcy. And for his work in that regard, along with the discovery of extrasolar planets, he and Mayor won the International Shaw Prize in Astronomy. Marcy went on to be one of the PIs on the Kepler satellite mission, which discovered over 4,000 extrasolar planets. And after that, he's also addressed, in fact, another issue that's relevant to understanding life in the universe, the possibility of intelligent life in the universe, the search for intelligent life in the universe. And he was a principal investigator on the Breakthrough Listen program, and more recently has considered the interesting question of whether we might use visible signals to look for extrasolar life instead of just radio signals, an area of research that he's actively involved in right now. Geoff and I discussed all of these important questions, and it's hard to think of a better person to discuss the search for extrasolar planets and their implications for life in the universe, perhaps, than Geoff Marcy, and I enjoyed the discussion tremendously. I hope you do too. If you want to watch it without ads, you can go to our Critical Mass Substack site and subscribe. Then you can watch it without ads. The subscriptions go to help support the Origins Project Foundation, a non-profit foundation that supports the podcast and other activities that help bring science to the public. Or you can go to the Origins Project YouTube channel and watch it there. Or, of course, you can listen to this podcast on any place you can listen to podcasts. However you listen to it or watch it, I hope you'll consider supporting the foundation in a variety of ways. And more importantly, I hope you enjoy the discussion that Geoff and I had as much as I did. Thanks. Well, Geoff, I'm very happy, really happy that you're finally able to be on my podcast. As you know, for many, many years, I've not only been a fan of your work, but I'm happy to say that I've gotten to know you better as an individual in the last few years as well. But I remember we first met many, many years ago when I was chairman of the physics department at Case Western Reserve, and you came to give a talk. Do you remember that?
Absolutely, very vividly, for all sorts of reasons. And I remember meeting you and chatting with you in your office.
And you were very gracious. I actually think you even gave me some slides. Those were in the days, I think, when we used slides. And I said, wow, I'd really like that image. And you said, okay, here's a slide. I think you gave it to me. And I was just shocked and impressed that you were. So you're very generous even then. By the way, I'm kind of wearing this shirt in honor of you, just so you know.
Amazing.
Yeah, because I'm going to talk about what it seems to me as I think about what you've done in your career, this notion of charge, not only just the little aliens, but the notion of charge, of basically boldly going, well, where no one has gone before, but boldly going in a way that, we'll just damn the torpedoes full speed ahead, as Richard Feynman once said, but someone else said it before him as well. And I want to, as this is an origins podcast, as you know, and I want to go back to your origins, which I've been learning about a little bit. You were born in Michigan, but you grew up in California. Is that right?
That's exactly right. Yeah.
Why? How old were you when you moved to California?
Four.
Oh, okay. Do you
All
remember
I remember,
Michigan? Yeah.
I remember being knee deep in snow in Detroit, in the suburbs of Detroit, and that's it.
Okay. Well, and then you quickly got out for Southern California, right? You grew up in Southern California?
Absolutely, yeah. My whole childhood, public education, the San Fernando Valley, but nobody's perfect.
Yeah. That's okay. Now, what were your parents professionals or were academics or what did they do?
Yeah, it's interesting. My mother majored in anthropology, got her bachelor's degree in anthropology. She used to talk to me about early hominids and the latest discoveries of hominids on the East African savanna. So I was very much imbued with the sense of sort of wonder about our own roots as a species. But my dad was a mechanical engineer, worked on thermal cooling systems, and he worked on airplanes, jets, and eventually later on the space shuttle
Wow. While you
as
were
an
a
engineer.
young kid or
Yeah, he would tell me about his. He was proud, of course, to have a contract, his group, of course, with NASA and helping with the cooling system. I think he told me he worked on the so-called auxiliary power unit of the space shuttle.
okay. I kind of almost know what that was because I was a nerd as a little kid, and I used to, well, I used to study the spacecraft. Well, I wanted to be an astronaut when I was younger, and I wanted to be the first Canadian astronaut because they didn't have them back then.
Yeah,
But and I think I wrote a letter. I'm not sure I ever sent it, trying to convince NASA what a coup it would be, what a public relations coup would be to have someone from another country. But I don't think I ever sent it since I was probably about 14 at the time. But anyway, but it's interesting when I hear this. So the combination of your parents is kind of interesting. Your own work in a way spans the two things. Your mother's interest in early humans and therefore sort of origins of life issues and modern humans. Your father's technical work as an engineer and your work in some sense has combined the two. Your technical work as an astronomer has led us to new thresholds about thinking about origins of life in the universe. So it's kind of nice how you've kind of merged those.
yeah.
Who
Well, I feel lucky about my parents, that's for sure.
did they encourage did they encourage your interest in science or how did that arise?
That's a good question, and the answer is yes, of course. And I can remember every afternoon and especially evening, they really required me to do my homework, and especially the science and math homework. So I would sit at my little desk in my little bedroom, and they would sometimes peer over my shoulder and make sure I did my homework and try to help me with my homework. But I can remember it. It's one of these situations where your parents are imbuing you with some set of values that you're not even aware of as a child. And I remember, now in retrospect, thinking, gee, they were telling me that my schoolwork was important and that learning the basics, English and math and a little science, was important.
Oh yeah, well, well. In fact, we'll get back. We'll probably talk about education later. We'll see where we go, but that that being taught to value those things at home, I guess, is really important, and it's affects people throughout the rest of their lives. And
Yeah.
but what made you want to do sort of physics and astronomy versus something else?
When I was 13 years old, I remember so clearly my mom and dad bought me a poster of the solar system, and it had the sun and then the nine planets, and it had some of the moons. I remember back then Jupiter had only 12 moons that were known. And
Yeah.
I put it up on next to my bed, and I would lie in my bed looking at that poster and thinking about how far away the planets were and how beautiful they were, and the rings of Saturn were unbelievably exquisite, and then the moons going around and around. And I just thought, wow, this is amazing. The distances are huge and we know so much. Of course, this was 1966 or 1967. But it really did throw me. Uh, I think for the long duration, about the beauty and the puzzles of the solar system and the universe at large.
Hmm. Hmm. Did you did you what about school? Did they encourage you?
You know, I went to public schools the whole time, elementary school, junior high school, and I thought my education was quite good. You know, I had teachers who seemed to be able to teach math and English, and I was lucky to take classes in, you know, in writing. So I was learning how to construct a paragraph, and then, you know, I took the usual biology and chemistry and physics classes. I wasn't very good at them. I was really sort of a B plus student. I struggled, but
Uh,
I feel very lucky that you know, in public education I had good classes.
well, that yeah, that's nice. I mean, the teachers were supportive. They basically encouraged you to continue. I was reading, as I've been reading about you lately, which has been kind of fun. Um, Somewhere, someone said that Carl Sagan was a hero of yours, and is that true?
He
I don't know if they
was,
made that up.
you know, he really was inspirational. Uh, I remember reading one or two of his books and watching him on TV, and I was especially impressed with the way he uh, married social justice issues, like the need for equality of all peoples, equality for across genders, and he was very interested in equality for all nationalities around the globe, and he looked at the whole sort of throw of history as sort of a long story of people uh, gathering together. He saw the human species as a sort of a team, and how we should try to pull together as a team. And he used to talk about what would the advanced civilizations say as they descended toward Earth and looked over the Earth and saw us squabbling in wars with discrimination and financial inequities and so on. And he argued, I thought, very persuasively and passionately, that we should pull together as a species and try to help each other.
Certainly, I mean, he tried to think globally in that in that way. With the Golden Record was certainly a good example of what of where he tried to
Right.
think about what would humanity as a species want to leave as an imprint in the cosmos in Voyager as it went out, if it was ever discovered. And I think that's probably the first time any organization officially tried to represent humanity, all of humanity, and not some country or not some individual. It was kind of an
Yep.
interesting
Yeah.
idea. One can
His
argue about
songs.
what they chose, but
Yeah, right, exactly. Well, yeah, I give him full credit for viewing we Homo sapiens as a sort of fledgling species in the galaxy, struggling, and we should try to, you know, encourage coherence and cooperation.
what you know? The other thing he did, I guess he was political. I mean, his work on nuclear winter, which, by the way, after the fact, was probably wrong, but nevertheless, it tried to raise attention and point to the yet another danger of nuclear weapons in a world that still has 10,000 over 10,000 nuclear weapons, far more than than anyone could ever
And
imagine.
another
You know,
theme that he raised repeatedly, which I loved, was he talked a lot about equality for women. And he talked a lot about the fact that over the globe, those countries in which the lives of women were improved and the education of women were improved, the those countries thrived, and they were financially better off, socially better off. So he was,
mm.
I thought, a passionate and wonderful advocate for equality for women.
Yeah, yeah, and we'll get to that because I know that influenced you in your younger days too, especially yeah, when you were a student in a variety of places. I was reading about that. Did you watch Cosmos? Did that have any impact
Oh,
or?
I loved Cosmos. Yeah, and there's some of those episodes are just indelibly, you know, seared into my brain. I thought they were beautiful. The overall philosophy of learning our place in the universe, how small we are, but indeed how important we may well be as an intelligent species and civilization. So he captured the grandeur and the puzzles, but also the sort of human spirit, you might say, of our human place in the universe.
Yeah, no, he was very grand, and I remember, um, yeah, I got to meet him a few times when I was at Harvard. He used to come to visit there, but I didn't watch Cosmos, maybe because I grew up in Canada, and so for me, it was another individual, Jacob Bernowski, who really had an impact on me in terms of under, the grandeur of the human condition and culture, but also the wonder and joy of communicating science, which, as you know, obviously, as you know, is something uh, that has been played a part in my life. But you have been well known, especially after your first discoveries, which gave you more of a platform, as being interested in communicating. Where
Absolutely.
did the example of Sagan, did that influence you? Is something you
Oh,
thought of doing when you were a young person about wanting to communicate science?
well, it's funny you mentioned that. You've reminded me of something I'd forgotten. When I was in fifth grade, my fifth grade teacher, Wayne Tate,
Hmm.
at Plummer Elementary School, he one day he came up to me and he said, "Jeff, I'll tell you what, you should be a teacher." And I've
Oh,
never forgotten that. I mean, out of the clear blue. And I don't know
yeah.
what it was about me that made him think that, but maybe he saw that I enjoyed helping other people and teaching them and connecting with them. And so, and then of course, Carl Sagan, as you say, resonated with that. And there were other great teachers. One I can't help but mention here is George A. Bell. He's he was a wonderful astronomer, professor at UCLA, and he got his PhD at Caltech and discovered clusters of galaxies, famous for the so-called Abell um, catalog of clusters of galaxies. But he was a passionate teacher, and he ran his own science school. And I was lucky to take two classes from him. And he also said to me, teaching is the greatest honor that you can do as a scientist.
Oh, that's wonderful. Well, we'll get to that because part of it was interesting to me that I didn't realize it at the time, but part of the attention you got for discovering exoplanets was due to the nature of the discovery. But I think compared to your collaborators and other people, people turned to you because you were able to talk to. In addition to having made the discoveries, were able to convey not only the excitement and passion, but talk about the science to journalists. And I remember that vividly the colloquium you gave at Case when I was chair. It was clear that that you enjoyed that sense of communication, that ability to do that, and that therefore made you a person that journalists would seek out, which I suppose at times, um, in groups of large collaborations, but people might sometimes feel jealous, or at least or some sense of that because people were turning to you. But in my experience, journalists have turned to people who will talk to them first of all, who are interested in talking to them and can convey the information.
Yeah, I mean, you've hit on a number of important topics there, and I do love teaching, and I get a lot of joy about it. Still to this day, yesterday I was teaching a fifth grade student about the universe and also how to play tennis. So I remembered even yesterday how much I enjoy and really feel it's our obligation as adults to be teachers as well. But as you pointed out, when your ability to connect with the broad audience, when that ability is great enough, people do turn to you, and that happened to me. And then I tried hard to make sure my collaborators got as much attention and credit, and I, frankly failed. I mean, I know that I tried hard, but I was not able to make sure that my collaborators um, got as much credit, as much attention, got their the accolades should have gone more to them.
Well, look, I mean, it's not your fault in a general sense because I've experienced this. Journalists want to pick an individual, and they always, you know, you probably had this experience too in the old days, but they always want to they want to make everyone seem like the next Einstein whenever they're a scientist.
Yeah.
And so it's not, and I'm not criticizing journalists in that sense. People like public interest stories and they want to turn to an individual. So journalists will naturally sort of hold on to that and try and try and glorify that in the sense, because that's what captures the story. And often that's what will interest their editors in allowing them to do a story. So it's
Yeah.
just a part of the problem of modern journalism that that they don't really convey science for what it really is, which is a team effort
Right.
in many ways, and also an effort of baby steps. Every new discovery is revolutionary and groundbreaking, and then, as I
Yeah.
say, the next Einstein. And they don't realize that all science is often done by lots of little baby steps. But that doesn't make for good headlines or good press or sell newspapers.
Yeah, that's exactly right. Yeah, it's very tricky, and obviously, what you're saying is that the public relations side of science is treacherous. We are sending, unbeknownst to us, a false message about the process of science, which often involves mistakes,
Yeah.
team efforts, false starts, blind alleys, and other people helping to redirect and eventually, hopefully, getting the right answer.
Well, look, I don't want to make it seem like it was just a cushy ride for you, because it wasn't, and I want to go back. I want to. So you went to UCLA, which was your local university, or basically,
That's right. Yeah.
and did physics and astronomy, right?
Yeah, I went back and forth between majoring in physics and astronomy, and eventually I just did both.
Yeah, okay. But astronomy clearly was your passion. I mean, you just at what point was it only into graduate school that you decided you wanted to do astronomy, or what point
Yeah,
did you decide?
well, what happened when I graduated with my bachelor's degree, I knew I wasn't smart enough to ever be a scientist. And I just thought I will continue the ride in physics or astronomy as long as the world will let me, and then I'll just have to be thrown out on the street. And I was very clear about that. And I applied to graduate schools thinking maybe I'll be able to get a master's degree somewhere. And I applied to both physics programs and astronomy programs. I got into a few of each, and I just felt lucky that UC Santa Cruz accepted me. A few other places did too, and I knew that astronomy was more my passion. So I thought, well, look, if I'm going to fail, that's fine, but I'd like to fail enjoying the ride
Yeah,
for
yeah.
the few years in graduate school, and then I'll go off and try to live a normal life.
Well, that's interesting. There's an important lesson there, in the sense that you recognize, which I think is that a lot of people look at the alternatives and don't and try and judge them. I see students all the time trying to judge them in terms of where they're most likely to get a job or the most money or something. And I always say it's just crazy to think of that, because first of all, you never know down the
Yeah,
line what's going to happen, and secondly, if you don't choose what you're most passionate about, then you're not going to be, not only you won't be happy, but you probably won't be as good in something else either. So if you choose a career path that you think is safer, well,
yeah,
it's all right to choose it later, but your whole life doesn't depend upon what you study at school. That's the one time when you can
yeah.
do what you really care about, and all the skills you might learn in astronomy or physics or anything else, or history or anything else, will later on be useful to you in whatever field
Well,
you
that's
decide.
for sure. And I remember thinking just what you said. I want to enjoy a few more years in school before I flunk out. But also, I knew that I was lucky with the education I'd already had. This is what you were saying. I
Hmm.
did have math. I had taken several years of math at the college level, UCLA. I took, many years of physics. I took some chemistry. I had some computer programming skills. I learned Fortran
Oh,
on my own, but it was not, it's not that big a deal, like how to write an if statement or
yeah.
how to write an equation down and solve for X. So, it turns out in the world, if you know English and you know a little bit of math and maybe a little science, you're good to go. You,
Yeah,
you
yeah,
can
yeah.
you can live a life that way and have a creative life and a life where you pay the bills.
Okay, well, you moved to Santa Cruz, which was known for its which had a very strong astronomy group and a
Yeah,
reasonable physics group too. And I think we've talked about this once, but we must have met, or at least we
yeah,
must have been in the same room many times, because the last year of my PhD, I did my PhD at MIT. but my
Yeah.
supervisor moved to Santa Cruz for that last year of my PhD, and I was and actually I taught a class um, with George Sand and a really interesting Matthew Sands, sorry, Matthew Sands, who was a fascinating and interesting teacher who had helped write the Feynman books, and
Oh,
and I
great.
sat through,
Right.
yeah, remember him, and I sat through many colloquia. I didn't sit through as many. There weren't separate astronomy ones. I guess there was a physics colloquia. There may have been. I didn't. I began to venture. It was a time in my life when I began to learn more about astronomy. So I heard those things. But we must have been in the same building at the same time because you got your PhD at the same time as I did.
And there was just one building that had both astronomy and
Yeah,
physics.
it's
Yeah.
that's interesting. Well, so there we go. We never knew we'd cross paths. It was
No.
a For me. It was I spent one term there, basically January on. No, no, I
Mhm,
guess I was no the whole year, the whole academic
mhm.
year, because I went there in September. I remember, and that's when I had to fly back east for an interview for the Harvard job, and Santa Cruz for me was a revelation. It was very different than anywhere I lived in Cambridge and in Boston, and um, but you went from there and you got I was happy to go move to where I did, but you got a nice fellowship at the Carnegie Institute, which is Mount Wilson, right?
That's right. Yeah,
and
exactly.
then and then you experienced a career issue, and I think that I wasn't aware of that, but I think that's really important that you not only had it but how you reacted to it. So maybe you want to talk about that a little bit.
Well, I think what you might be referring to is when I got to the Carnegie Institution, I felt like I was surrounded by brilliant astrophysicists, and I knew I wasn't. And I kind of felt like it was a mistake that I had gotten the Carnegie Fellowship in the first place. And indeed, my PhD thesis topic, which was to measure the Zeeman effect in stellar spectra, was floundering, and it had run its course. And I was desperate to find some other type of research to do for my remaining year and a half. And I couldn't think of a good project, and I got more and more depressed. And it was pretty serious. I remember waking up in the morning and I felt so terrible I couldn't get out of bed. I just lay
Wow.
there thinking feel sick, and my head was hurting. And I remember asking myself, knowing that I was sort of inadequate in this uh, world of Carnegie Institution with Caltech next door, I started wondering, whether I was actually suicidal. And I remember
Wow.
asking myself that, am I going to commit suicide? Because what will my parents think? What will my friends think if I can't succeed as a scientist? And I was lucky. The health plan they had allowed me to go see a psychotherapist, and I went. It was at Kaiser downtown Los
Hmm.
Angeles, and for I don't know 4 or 5 months, I went every week. And in brief, the guy I saw, I was lucky. He basically pulled me out of the depths, and he said, "Look, you've got to have a little more self-esteem, and you've got to somehow enjoy the ride, and whatever happens happens, but you've got to find some pleasure in whatever it is you're doing, and you may end up opening a new chapter later on." And that allowed me to at least survive.
Oh yeah, that's fascinating. Again, there are hard periods, well, and this is probably worthwhile for students to know. I mean, there are hard periods in life. It depends. I mean, graduate school itself can be a very difficult time. I know it was for me in some ways. The feeling of, especially if you come, I went to a not small school in Canada, and suddenly I was doing my PhD at MIT, and it was a question of whether I could compete and whether I was good enough, and then the misery of sort of working as a graduate student, and as I remember someone saying, there's light at the end of the tunnel, after you get your PhD. But then when you get your PhD, you have to then sell yourself,
Yeah, you have to do
and
something.
and it's hard. You have a limited amount of time, and it's a very stressful period for
It's
people.
stressful, yeah.
I
I,
you know I had a I mean I wasn't in that situation, but I remember, I guess you have two choices. You either have the imposter syndrome or Dunning-Kruger syndrome, and it's better to have the imposter syndrome, namely to feel like hey, maybe I shouldn't be here, than to not recognize at least your own inadequacies in some ways. And Yeah, I remember at Harvard, suddenly for me, it was like I was in the same environment. I was at MIT and I
Yeah.
moved down the street to Harvard and I'd taken most of my classes at Harvard. But suddenly when I got this fancy fellowship, this Harvard Junior Fellowship, suddenly everyone knew who I was at Harvard. And I was the same person as I when I've been a graduate student, but suddenly I felt like, well, suddenly they know who I am and I'm supposed to be well, but I haven't done anything. and
Yeah.
and I really, for about 6 months, I had a really difficult time working because I thought, well, I just
Mhm.
I shouldn't be here. And then, you know, then I just said, okay, I'll just work. And
Yeah.
but you recovered from that with the assistance, of course, of some good help, which is important. But I was reading, and again, I don't believe everything I read, but that that you said to someone in the shower or something that you really decided, hey, if I'm going to fail, I want to do something spectacular. I want to fail spectacularly rather than not, just doing stuff. And that choice, I think, is a remarkable one. So maybe you want to go into it.
Well, yeah, it was a little different than that. I do remember very clearly standing in the shower one morning, barely able to get out of bed. The water from
Mm,
the shower is falling over
mm,
me, and I was very depressed. And I thought, I have got to pull myself out of this. I'm obviously going to fail as a scientist. Okay, that's a given. But I still have a year and a half left on this Carnegie Fellowship. So what am I going to do? And I thought, well, great. If I'm going to fail, I might as well try to answer a question that is so meaningful to humanity and to me as well, that at least I'll go out trying to do something that is has a human component to it, not just sort of the physics dry scientific aspects. And I realized with the water still falling over me that I wanted to know if there were any other habitable worlds out there, and if any of those worlds might in fact be inhabited. And I remembered then something that was a failure of mine back in Santa Cruz, which was my advisor, George Herbig, asked me to measure Doppler shifts in stars. And the brief version of the story is I failed at
right.
that too. I tried to measure the Doppler shifts and I came back to him with the results. And he said, Geoff, your errors are about 3 kilometers per second. Why are your errors so large? And I didn't know. And he didn't know, which was more impressive. But I
Yeah.
didn't know. And it stuck with me. How can you make a measurement and not know what your uncertainty is? And there in the shower, I realized, okay, if I can measure Doppler shifts more precisely, I can detect the wobble of a star as it's yanked on gravitationally by any planets, but I have to measure Doppler shifts more precisely. And so I thought, okay, I'm going to spend the rest of my time as a postdoc trying to measure Doppler shifts precisely enough to maybe detect the largest types of planets or brown dwarfs.
Okay, this is great. So you decided this was a scientific question, and again emerged. I mean, this fundamental question: Are we alone? In a sense,
Yeah,
which 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 Sagan, of course, it had asked as
yeah,
well, and everyone's asked at some point in their life.
yeah,
And it's really bold, but it's not going to be. But the fact that you were saying, it's going to be clear that it was not going to be easy. So it was not going to be the type of thing that could be done in a year and a half. But you already chalked off your career, so you said, okay, doesn't
yeah,
matter. It's not something I can necessarily get to, but it's what I'm going to try and work on. But you went when you went over this. For many people watching this, they will not have the slightest idea what a Doppler shift is. So let's
right.
uncompact that a little bit. Yeah. So um, let's just describe why one might want to measure Doppler shifts and what they are. So
Yeah,
I'll give you a chance to start.
yeah, this is well known to astronomers, but it's easy to explain. When a star emits light, that star might be coming at you or moving away from you, and we collect the light from that star. But the light waves get a little compressed if the star is coming at you, and indeed, if the star is going away from you, the light waves get stretched out as the star recedes each time it emits a wave crest. We all know this effect in sound when the race car goes by you, you hear meow. And so that's the Doppler effect in sound. And the same thing happens with light. So you can determine if a star is coming at you or away from you. And even more excitingly, you can determine if the star sometimes is coming toward you and then a little later away from you and then toward you and away from you and toward you as the star is being yanked on gravitationally by any planet. So this
That
is a way, and a well-known way, to detect unseen orbiting objects around stars.
had it been used um, to detect binary stars, stars going around each other?
Absolutely, going all the way back to the early 1900s. And there were even papers, indeed by a guy named W. Campbell. I found the paper where he says, currently here, and I think it was around 1908 or 1913 or somewhere in there, he said, clearly, if we could measure Doppler shifts more precisely, we would be able to detect not only small stars orbiting other stars, but we would be able to detect small planets. He actually explicitly said that. So this was a concept known for 60 years or something prior.
And this itself, by the way, not only so Doppler shifts that are that, and it's a different reason for light than sound, but it's the same idea, and we call it a red shift or a blue shift.
Right,
Red being if the star is moving away from you because the radiation gets stretched out, and red is the longer end of the spectrum, and if it goes towards you, blue is a shorter wavelength, and so it
right.
gets scrunched up. So we call it blue shifts or red shifts. Those are the terms astronomers use. But uh, interestingly, within that concept, that it also flies when kids go to school. They learn the Earth orbits the sun if they went to go to a reasonable school,
Yeah,
especially since the Copernican revolution. And and but of course, it's not true.
it's
It's
not
the Earth
true.
orbits the sun, but the sun also orbits the Earth. But the sun's orbit is much smaller than the Earth's orbit. The point is they orbit each other, and because
Yeah,
the sun is a lot heavier, a million times heavier than the Earth, as the Earth goes around the sun does respond. But this is the point, and this is why I figured it would what you were doing would be never be possible, because the
yeah,
sun is a million times heavier than the Earth, and therefore, in a sense, its response to the force of gravity of the Earth pulling on it is at least a million times smaller, and
right.
therefore the Earth goes around the sun. The sun is doing a motion, but the motion is unbelievably slow. And who the heck could do this? I mean, I think our sun
Yeah,
is the speed of our sun as it moves in its little mini orbit as the Earth
right.
goes around it is something like, am I right? It's something like 10 meters per second or 8 meters per second or something
Well,
like that.
there's two answers here. The Earth, as it goes around the sun, causes the sun to move with a speed in its little mini
Yeah,
orbit, as you called it,
yeah.
by 10 centimeters per second.
10 centimeters per second.
Yeah.
Unbelievable.
So,
Okay.
in other words, sort of the speed of a caterpillar on a leaf,
Yeah,
basically.
that's right. And so
I mean,
I mean, that's the reason I would
you have to
say,
measure that speed of a star that's
yeah.
about 1,000 light years away to to plus or minus 10 centimeters per second.
And
Ridiculous.
it's ridiculous. And I want to stress that because that's how bold the challenge that you decided to face, and
Yeah.
why I've talked about this in different contexts. Why, as a theorist, would have said, "No way am I gonna, no way, I'm not gonna try that." I mean, it's too difficult. The idea of
Well,
somehow being able to measure a speed that's much smaller than the speed you can walk of a star far away, but you decided to try and do it, and so
and it's worth mentioning here for people who are young and thinking of becoming scientists. It's very helpful to think about challenges in science that seem unreachable to the old folks. But if you have a little bit of a clue about how to do better technically than people did in the past, you can reopen that question. And in my case, I remember telling senior astronomers that I was going to search for planets by measuring Doppler shifts, and they were all embarrassed for me. They literally looked down at their shoes and scuffled their feet, and there was a little faint smile to try to be polite. But they knew I would fail, and even as recently as the early '90s, my fellow astronomers would look down at their feet and sort of smile politely. So it was just well known, for the whole century of the 1900s, that nobody would ever find planets. They just don't have any effect on anything,
okay, and that was
supposedly.
Okay, exactly. And I love when conventional wisdom is shown to be wrong. And I think you made a point, which is another point I try and stress, and we see it in a lot of discussions I've had with scientists, and which is that, and I've told young experimentalists this as well. Every time we can open a new window on the universe, we're surprised. So science is an empirical discipline. I'm a theoretical physicist, and sure, that gets a lot of attention, all the weird
Yeah,
ideas we come up with. But science is an experimental field.
yeah,
It's based on experiment. It's driven by experiment, or in this case, observation. And if you can find a new technique,
yeah,
use it. You may not know that, hey, there's no obvious application of this technique, but if history is any guide, if you have a new technique, it's going to be useful somewhere in science, and it's really
yeah.
interesting. Why
And
I'm
we're
so
and
envious, I
we're
guess.
Yeah, exactly what you said. And we're lucky in astronomy. We ride on the technological advances of the rest of the world. So when the rest of the world invents a new type of camera or a way to form optics, or maybe make larger computers, all of those things allow critical, vital leaps forward in your ability to make the measurements of the universe that simply weren't possible before.
Yeah, it's truly amazing, and as I say, it sometimes makes me jealous as a theorist that knowing it, the experimentalist gets a new technique can push it, and but to some extent, this the same thing happens, but much less often in theoretical physics. Einstein's new technique of learning geometry, which he had to learn, or Feynman's development of new techniques. But
Yeah,
a new observation, and that's why one of the reasons why kids have asked me, what's a good field. Well, the one of the reasons astrophysics is a good field is it's a golden era because it seems every year there are new techniques that come up that you allow you to do things you would never have imagined you could have done
right.
uh, 10 years ago, much less 40 years ago.
Yeah.
And
Right.
so you knew, so you started to go back to you now. You started to look at ways to improve your ability to measure these Doppler shifts from kilometers per second
Right.
to centimeters per second. And for people, a centimeter is what 1/100th of a meter, and a kilometer is 1,000 meters. So you're talking about an improvement of a factor of 100,000. It's not a factor of two or
Yeah,
five or
right.
100,000.
Right.
And so what did you start doing?
Well, um, there were several steps that I never foresaw, but they were turned out in the end to be very important. So there I was, of course, still as a Carnegie Fellow, using the Mount Wilson 100-inch telescope, the venerable telescope that Hubble had used to discover the expansion of the universe. That's a daunting thing, by the way, to
Yeah.
walk by the locker that says Hubble on it, and walking by. And
Yeah.
what happened was I started using the spectrometer that was there, and I tried hard to trim all of the errors that I thought were causing the trouble, and I identified a few and got the errors down to about 200 meters per second, which was already a factor of about 10
Yeah.
better than I had been doing while I was a graduate student. And I ran into a really amazingly brilliant astronomer who hardly anybody knows. His name is Roger Griffin. And he said, "Oh, Jeff, your problem is that when you guide the telescope and put the starlight into the spectrometer, the starlight moves around. And so you have to prevent that." So he actually gave me yet another clue that it was the motion of the star image that is a problem.
You mean naming the fact that the apparent motion due to jittering of the telescope?
Exactly. Yeah, and the Earth's atmosphere, which causes by refraction, causes the star to dart around. And
Yeah.
it's very obvious when someone
Mhm.
tells you that, you think, "Oh, of course, why didn't I think of that? If the star's moving around, the whole spectrum moves around, so it mimics the Doppler shift."
Yeah,
so
of course.
so I had to
So
figure out a way to get around that. And I'll jump to the next stage, which was really wonderful. And this is a great story in and of itself. There is an obscure astronomer named Bruce Campbell. Nobody's ever heard of him. He was a postdoc himself, and he and his collaborator Gordon Walker invented a new technique to get around this motion of the star. They also realized it. Maybe they talked to Roger Griffin too.
Hmm.
And what they did was, in brief, fill a glass container with hydrogen fluoride gas. And as the starlight passed through the hydrogen fluoride gas, it the light from the star picked up additional absorption at specific wavelengths, i.e., colors,
Hmm.
specific wavelengths that indelibly marked the wavelengths right on the spectrum. So even if the whole spectrum Doppler shifted, or sorry, if the whole spectrum shifted inadvertently, those absorption markers due to the hydrogen fluoride gas marked the true wavelengths of the light. And when I learned about Bruce Campbell's idea, I thought, we've got to do this and we've got to do it better, at least a factor of 10 better than he's doing it. And that's what led me to ask the solar physicists what they should do. And a friend of mine, a solar physicist, Dave Bruning, said to me, we use iodine gas. And so I told my student, Paul Butler, who was absolutely brilliant, I said to Paul, we should think about iodine. And he went off to the library and he checked other molecules and he came back and he said, yep, iodine is the best. So we developed this whole technique that no one ever heard of putting iodine gas in a telescope. I mean, it's the
Wow.
craziest thing. But the iodine gas then allowed the starlight to come through and pick up thousands of absorption lines, as we call
Uh,
them, markers in
uh.
wavelength. And that was the wavelength calibration that allowed us to measure Doppler shifts to within 10 meters a second.
Okay. Okay. So that within tens of meters per second. So that, and that, but that idea took time. I mean, the point is, I want to go back because Paul Butler was your student at San Francisco State University, which
Right.
at the time was not a major research institute. You didn't have a PhD program, right?
I went
You,
there because I wanted to be a teacher.
yeah, you went exactly. It was a teaching institution, not so much a research institution. So you were cobbling together this kind of effort, and and this is the other important thing. This is what year did you go there? 1982, 84, 3 or 84,
84, yeah.
84,
84. Yeah.
and you're there, for a decade working
Yeah.
on these kind of techniques to try and continue to improve it sort of on not quite on the side, but I mean, sort of on the side because it's a teaching institution.
I
And
was teaching 3 classes every semester.
wow,
I
I don't know how
taught,
many.
and I enjoyed the teaching. As I said, I mean, it was a real pleasure. I taught electricity and magnetism. I taught statistical mechanics. I taught astrophysics labs. And that's more or less a full time job. But of
Yeah,
course,
yeah,
I worked evenings. I worked weekends. I wasn't yet
yeah.
married, and so I had lots of time. And Paul is absolutely brilliant. He's still working to this day. He's an incredibly hard worker and very innovative, and he's dedicated to working as hard as he can to get the right answer. And
But
you know,
he it
it
was a
worked out.
wonderful it was a wonderful, like many things, it was fortuitous collaboration of
Yeah,
a really good student and a dedicated teacher and a great
yeah.
scientist is working hard. But was Putler doing a master's degree because there was no PhD
He was
program at
doing
the
That's right. He was doing 2 degrees, a bachelor's degree in chemistry.
ah
That's important because we needed iodine, and
yeah.
a master's degree in physics.
I see. Well, it's just the fortuitous, and then and you continued to work. You must have gone on to do a PhD somewhere else while you were working with him,
He did at
or
Maryland.
at Maryland. Okay, and but your collaboration continued during that period.
Oh, absolutely. Yeah.
Yeah, and so you came upon this new idea, and that allowed you to reduce the uncertainty from 200 meters per second to
10.
10 meters per second.
Yeah.
Okay, and now 10 meters per second is already interesting, and I already kind of gave it away in a way because the sun doesn't move with respect to the Earth very much, but the Earth and the sun aren't all there is in the universe. There could be other things, and
Yeah.
so one could work out that maybe, um, actually, let me ask you this question because I used to know the answer and I could work it out. But due to Jupiter is 1,000 times the mass of the Earth,
Exactly.
and it's pulling the sun, therefore, more strongly than the Earth is. How much does Jupiter make the sun move? How
So
fast does?
Jupiter, when it goes around the sun, takes 12 years, but it
Yeah.
yanks the sun around at 12 meters per second. That's a
Aha.
lot. That's a lot more than 10 centimeters per
Meters per
second.
second. So
And
suddenly
of
meters
course,
per second. Yes, sorry.
and
Go on.
this was, this was a breakthrough for Paul and me, because we knew that our Doppler precision was 10 meters a second. We could tell if a star was a coming or a going at 10 meters
Yeah.
a second. And a Jupiter-like planet around another nearby star would cause that star to move at 12 meters per second. So we would just barely be able to detect Jupiter analogs around other stars.
Except, of course, you'd have to have a pretty long career, because the other problem is that if you're looking for repetitive motion and the orbit is 12 years, you
Yeah.
want to see a bunch of orbits. You've already got two orbits take 24 years.
Yeah.
That's a long time to get data. So
And you need two orbits, because one orbit goes by, nobody will believe your results. So the most important ingredient, I used to say, was not the telescope or the iodine or the computers or the technique. It was tenure.
yeah, that's right. It was tenure. It's the fact that you could, once you had tenure, you could afford to work on a project for 20 years. And I think people don't
Yeah.
realize how important that is the
Yeah.
idea that, um, for some things you can have a breakthrough right away. Other things require decades of work. And it just
Yeah.
depends upon the field. I don't know if ever, I ever told you a story. I'm sure I've said it to someone else about, maybe on this program, about Dirac, who was a very, obviously one of the smartest physicists of the 20th century, but also very laconic and did not talk. And when he went to do a postdoc, um, I think it was with Bohr, and and uh, and Bohr asked his supervisors. I think it was that way. Back at, I think he did his work at Cambridge. This guy's, he sits in his office. He hasn't done anything. And then the supervisor told a story about this parrot in a store that's being sold. And I won't go into, it's a good joke, but basically this guy goes in the store, wants to buy a bunch of parrots, and there's beautiful parrots that are worth $500. And then there's this ugly parrot sitting in the corner, and he says, what about that one? He goes, oh, let's not talk about that one. And he keeps so finally he convinces them, what about this parrot? How many words does it speak? Oh, none. Well, it's not very pretty. Well, what's its price? Oh, it's $500,000. And the guy goes, what? It's not pretty. It doesn't talk. And the guy goes, yeah, but that parrot thinks. and, and so I think the point is that, sometimes one of the problems of our educational system in its way with the postdoc system is that and happily tenure helps with that, but you got to get to tenure, is the fact that some project problems are so difficult that it takes a
Yeah.
long time to make a breakthrough. And unless that's appreciated, it's hard. And with our publish and perish society,
Yeah. Yeah.
it's really difficult. But luckily you had tenure at this teaching institution, and we're able
Right.
to say, what the heck, I'm just going to plug away. And you
Exactly.
plugged
Yeah.
away, and for a decade or more. And
Yeah.
then there was a race. And then what happened? Talk to me about
Well,
1995 and that period
people
then.
think it was a race, but we all thought we were going to fail. Nobody thought we would actually discover planets. My good friend Gibor Basri, at UC Berkeley, would say to me, look, he was trying to calm me down and temper my probable disappointment. And he would say, surely you realize you're not going to find any planets. And he was right in a way. It was a long shot. And after decades of people failing to discover planets, why should we be able to do it suddenly out of nowhere? And of course, I would explain to him, we've, trimmed our Doppler errors and so on. But there was still a widespread uh, skepticism that planets would ever be discovered. And so it wasn't really a race. There were actually many groups. There was a great group at Harvard, another one at Texas led by Bill Cochran, a guy named Bob Noyes at the Smithsonian
Mm-hmm.
Institution working on it. Brilliant, wonderful man. And um, our little fledgling group at Little San Francisco State. And I knew of the group in Geneva because I had read the papers by Michel Mayor, and I had met his student Didier Queloz at a meeting in Garking, in Germany. And so, I knew that there was interest in measuring Doppler shifts more precisely at these different places, but we were all just piddling along
Yeah, because you
until
didn't know.
1995.
Yeah, and then the world changed, not because of a new technique which you guys had developed, but because of the fact the world was stranger than you thought it was, which is the
Well,
other wonderful thing about the world. Just hold on though, because I want to turn off this light to see if it affects the buzz I'm hearing. But
okay.
and I'll tell Corey
Yeah,
to edit this part out. So I'll be right back. Hold on.
sure.
It didn't, but it made it cool. Making it didn't, but it's making it cooler for me. So we'll go
The
back.
buzz might be on my end.
Yeah,
So,
it's all right. No worries. Well, now, so the world, as I say, the world turned out to be stranger. That was the other gift. I mean, there's two great gifts for scientists: new techniques and the fact that nature has a greater imagination than we do. And no one,
right.
when I, when I was younger, when thinking about other solar systems and estimating the probability of life, the natural thing is to assume we all, and it's the reasonable assumption is that you're typical, is that your situation is typical,
Yeah,
so that
absolutely.
if you want to investigate situations you haven't seen, to assume if you're looking out into the unknown that 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 what you where you're that you can base things on your circumstances, and it turns out we're not typical. So talk about that remarkable discovery which occurred in for a bunch of you, that
Yeah.
taught you that hey, things aren't what we thought.
Well, I'll back up and restate what you said. There were people who worked on the theory of planet formation, and their job was to determine what planetary systems might be like around other stars, and they used theory, how dust and gas collects gravitationally and coagulates into planets. One of the most famous was by a guy named Alan Boss, and he predicted that Jupiter-like planets would all form at Jupiter-like distances
Hmm.
around their stars. And it was a very formal theory with hydrodynamics and gravitational forces and hydrodynamic waves traveling through the gas, and he predicted that Jupiter's sure enough would form so far away from the star that they would look a lot like our own Jupiter. Well, with that as the backdrop, of course, Paul Butler and I were tooling along, improving our technique, thinking that the orbital periods would be 10 years or 12 years. That's how long it would take the Jupiters to go around. And one day I got an email in 1995, October 1995. I got an email from a physicist named Phil Morrison. Now, you might know Phil, but
Not
nobody,
Philip, not the Philip Morrison.
the Phil Morrison.
Yeah,
And
who's
and
one?
he was on leave at Edinburgh, and he sent
Oh,
me a nice email. This is again October 95. He sent me a nice email saying, "Geoff, I've just gotten a rumor that someone is going to announce the discovery of the first planet ever. It's Michel Mayor giving a talk in Florence, Italy. Do you know anything about this rumor?" And I didn't, but I immediately thought to myself, first, here we go again. Another false claim of a
yeah.
planet found like Barnard's star. But
Hmm.
my second thought was, wait a minute. I know Michel Mayor. He's one of the most careful observational astronomers ever. And so, if anybody might have it right, it might be Michel Mayor. He gave the talk in Florence, he announced the planet. It was denounced immediately by most of the astronomical community. They said that he had fooled himself. The star was either pulsating or maybe it was wobbling in a face on orbit due to a stellar companion. Um, but it was very lucky what happened. Paul Butler and I had telescope time at the Lick Observatory 5 days in the future. And just by sheer luck, we had 4 consecutive nights on that telescope, and the supposed orbital period of this supposed planet around 51 Pegasi was 4 days. So here we just happened to have telescope time later in the week with a string of nights exactly equal to the duration of the supposed orbit of this planet. Of course, we were also lucky it was clear every single night. We
Yeah.
got Doppler measurements every night. Paul worked the computer and measured the Doppler shift. And by the end of the 4 nights, we saw exactly the wobble, a sine wave in Doppler shift up and down at the end of the 4 nights, bang on what the Swiss team, Michel Mayor and Didier Queloz, had said. And I remember to this day, Paul and I drove off the mountain, Mount Hamilton, where we had used the telescope, and we were just silent. We were both astonished and really ecstatic that somehow the first planet had been found and we had been fortunate enough to play a role in confirming it.
That's one of the wonderful things that I think about you, having come to know you, Geoff, is that generosity of spirit. Well, I remember when I first heard about this, I heard that your first response was ecstasy. And it wouldn't have been the first response of a lot of people. I think, you know, uh, uh, it takes a big sign. I remember when, of course, when when the cosmic microwave background was discovered, the people who were really looking for it were didn't get to see it first. Jim Peebles and Wilkinson and the leader of it, who's one of the greatest um, experimental physicists around, who's, oh my God, he's gone for a moment. Anyway, but and these guys at Bell Labs had accidentally discovered it, and I remember him. The leader of that group of Peebles and Wilkinson was why is my mind? Oh, he's a great scientist.
He's the
And
one that did gravity experiments.
yeah. But anyway, it'll come to me again when we're
Wasn't
talking.
he Virginia Trimble's husband?
No, not that guy. No,
Oh,
no,
okay.
not that guy. No.
Okay.
No, this was a truly fantastic
Be
experimentalist and
careful with
made
your words.
breakthroughs in a wide variety of things, and people don't know
Ah,
who he is, and I feel bad that I forgot
yeah.
the moment. But anyway, the he came in and said, "Hey guys, we've been scooped," and it was like with a smile, and they were gracious about it, and they were great
Hmm.
scientists. But the fact that you felt ecstatic, I again, I remember, I remember in various times in my own career, when I'm working on something and you discover, and you're writing a paper, you discover someone else has just written it. The feeling is not always ecstasy, and so I think it's wonderful that
Right.
you felt it wonderfully a part of it. But the point then is that it wasn't as if you could just be observers, literally, where you were observers, but not observing the phenomena elsewhere. Because you developed these techniques, not only could you immediately confirm that, but you became the leaders in discovering new planets. I mean, I think something
Yeah.
like 70 of the first 100 planets
Right.
that were discovered by you guys, right?
Yeah, that's exactly right. We were lucky because our technique using iodine gas really was fantastic, and it offered a higher Doppler precision than the Swiss team had, and so it was kind of a shared joy because we could contribute so many of the next planets, confirming the types of orbits, the eccentricities. Some of the planets were in close, and of course that's the strange thing about
Yeah.
51 Pegasi was 4-day orbital period, whereas our own Jupiter takes 12 years to go
Yeah,
around the sun.
that's
So,
that I mean I you're right. I passed over that. I was going to get to it, but the fact that fact, we almost just, it came upon as a side thing. Yeah, the period is 4 days. Well, that's not surprising. But of course it is. The Earth's
yeah,
period around the sun is a year, and here's a Jupiter object going around the sun in 4 days, which
right,
means it's far closer to its star
right.
than Mercury is. It's unbelievably close. It defied all the wisdom of what makes a solar system a solar system.
And the first calculation I did, which is what anybody would do, is you would ask, is a Jupiter that's that close to its star
Yeah,
stable?
yeah,
Maybe it'll heat up and evaporate away. So you can quickly do that calculation of the thermal equilibrium of the planet and what the escape velocity from the gravity of the planet, and you can calculate how much of the gas is going to escape every year and how much will be left after a billion years. And sure enough, the planet is stable.
it's amazing. Again, it's another thing. If you asked my gut feeling, I would have said such a planet that close would not be stable. The
Right.
tidal forces would strip it. By the way, I remember the guy's name. It's Bob Dickey, of course,
Oh, Bob
and
Dickey. Yeah.
he was
I thought
probably
he
one. Dickey, Wilson, Peebles, and Wilkinson were the ones who were, and they were all each one a truly great scientist. One of the sad things, in a way,
Yeah,
that they passed away. Well, that they didn't get that particular Nobel Prize. Not that it matters, but
yeah,
Dickey was an amazing man. But anyway, so go back to
yep,
this:
yep.
the fact that another surprise, not only that that it was there, but that it could be stable there. And then the question is, how the heck did it get there in the first place? And and um, and that originally, so it's not only, I mean, confirming the existence of a planet around a star is one thing. Although I think it's fair to say, I know at least from my own experience around that time, that astrophysicists all suspected there were lots of planets around lots of stars. If you make stars on a computer, you get this accretion disk and it
Right.
fragments. And generally, you're going to expect a solar system, but no one had ever seen it. But so just seeing a planet around a star is maybe it's a remarkable observational discovery, but you might not be surprised. But this discovery at the same time revolutionized the thinking about solar systems. It was two things at once, and it was
Well, let's back up a little bit because I'd like to just offer a slightly different
good,
rendering of history.
good,
When that discovery was made, very few astronomers believed it.
sure,
Um, I can tell you many stories, visits to Caltech, where astronomers would draw me aside and say, that 51 Pegasi discovery is not right. And here's what they said. They said, first of all, um, the so-called planet might have actually been a small star in a face-on orbit, so nearly face-on that the Doppler shift, which only accounts for the motion toward you or away
mm-hmm.
from you, is very small, not because the object orbiting is small,
Mm-hmm.
but because the orbit is so face-on that the star
Mm-hmm.
is hardly wobbling to and fro. So that was a very widely espoused theory for 51 Peg. Another theory was that the star itself was pulsating, getting bigger and smaller and bigger and
Mm-hmm.
smaller. So you would see the Doppler shift. We went for 2 years with many people thinking one or the other of those was the right answer. And indeed, there was an interferometer, so called, on Mount Palomar that made measurements of 51 Peg and saw it wobbling as if it really was a face on orbit.
Uh, uh,
When I learned that, I was sure it was wrong, but I was probably the only person, and I can tell you why I was sure it was wrong. But it gave everybody an excuse to say, 51 Pegasi is wrong. And I'll tell you one last thing. The paper that Michel Mayor and Didier Queloz sent to Nature about the discovery of 51 Peg
mm-hmm.
was rejected.
Yes.
The paper was rejected, and I learned about this. I was not the referee. I can tell you. I know who it was, and the referee correctly, I think, or at least consistent with the sociology of the time, said, "Look, this is not an adequate defense of the claim that it's a planet." Now, of course, 5 days later, Paul and I went up to the telescope and we saw the same effect. And that doesn't prove that it's a planet. It still
Yeah.
could be a face on orbit
Yeah.
or pulsation, but at least it gave nature the impetus. So, of course, the journalists descended on Paul and me. We showed them our Doppler shift measurements, and nature changed its tune. And they published the paper by the Swiss team, which of course was the correct thing. I remember it's a cute little story. Michel Mayor was panicking because he learned that we had found the wobble effect.
Mm-hmm.
And he called me on the phone from Geneva. And there I was in Berkeley at the time. And he called me up and he said, Geoff, I have a very urgent request for you. Would you please not publish your paper? Nature is refusing to publish the paper. Would you please just not publish the paper until we can publish our paper? And of course, I said, "Of course, Michel, no problem. No, not we wouldn't even dream of doing this." So it was just a cute moment. And what was interesting, if you don't mind my droning a bit, was we went for 2 years with most of the astronomy community doubting that this was really a planet, and that's science at its best,
Yeah.
right? You make an extraordinary claim, we started finding planets, and the community dragged its feet until they got better confirmation.
Well, extraordinary claims, and it wasn't Carl Sagan the first person to say this, but he
Right.
popularized it. Extraordinary claims require extraordinary evidence. And so it's not, people may say, oh, scientists are closed-minded, but it's reasonable to be skeptical. Most exciting new discoveries are wrong. And if they
Yeah.
weren't, we'd be getting one a day, and so it's reasonable. But what ultimately caused the sea change? Was it the fact that you discovered 70 of these? You see, one observation can always be anomalous.
Yeah.
One observation could be a system which is accidentally face on, but 70 of them, it's not likely you're going to get that same accident. What
Well,
caused that sea change in the community?
so there were two breakthroughs. Um, David Black, who doubted the planets, said to me in Houston, I will never believe these are planets until you find at least two of them going around a star. Planets come in groups. Yeah, maybe there was a protoplanetary disk, but if these are really planets that you think you're finding, there should be two or three or four until you find a system. I'm not going to believe these are more like binary stars, where the second star is a puny one. And then, luckily, in 1998, we did discover a triple planet system around Upsilon Andromeda. It was wonderful. We found one planet, then we found a second, then a third. We worked with the Harvard team on this. It was great. And those three planets, I think, offered a lot more assurance that these planets we were finding were at least kin, maybe not close kin, but kin of the planets in our own solar system. The real breakthrough actually occurred in 1999 when we finally found one planet that we had been anticipating that orbited the star and crossed in front of the star, dimming it, and that cinched it. And that was Greg Henry, by the way, who made that discovery, and Dave Charbonneau made it independently. When Greg and Dave found that transiting planet, it was HD 209458. For those of you who are interested, I'll never forget it, because when we predicted when the dimming would occur. Imagine you make Doppler measurements,
Yeah.
the
Yeah.
so-called ephemeris. When that planet should be in front. And Greg Henry did the photometry, measured the brightness, and the star dimmed exactly when and by the amount that it should have if it was a Jupiter crossing in front. So
You
that removed all doubt.
it's interesting. You anticipated where I was going to go next, because no, it's great. And that's, first of all, that's a new technique, right? You have the
It
technique of the
was.
wobble, and then you have another technique which I also would have said and not
Yeah.
believed. I remember, I think the first time I saw it, I probably didn't believe it either, because I would have said, pshaw, you can't measure a star moving at the same speed a
Yeah.
sprinter is moving, 10
Right.
meters per second. But then I
Right.
would say, look, this puny little planet in front of a star is going to dim it by a little bit, but stars are variable, and who would
Right.
believe that you could do that? And so it's another technique that, again, as an outside ignorant theorist, I would have said, ha, no way. But the fact
Well,
but again, I think the point was that not only did it happen, but it happened with a kind of regularity that was exactly what you predicted, I think, is the
yeah.
more important aspect.
Well, and again, it's probably worth going back, because this is, I hope, inspirational for young scientists. In retrospect, the Doppler shift we measured for some of the planets was so large it could have been done in the 1960s. It's
Uh-huh.
just that nobody expected Jupiter-sized planets that close to the star. And similarly, when a Jupiter goes in front of a star and blocks some of the starlight, it dims the star by 1%. Okay, 1% is a small number, but it's measurable. So, in fact, in the 1960s, people could have discovered planets. You would have had to look at a few thousand stars, but sooner or later, you would have seen one that dimmed due to its planet.
Actually, that's probably, well, that's an interesting thing, which probably it's not so much the telescope capabilities as computational capabilities. One of the things that was a big development, which came
Huge.
in the 70s, 80s, and 90s, was the ability to look at 1,000 stars, not just one star. The ability
Right.
to do that with the optics and the computer technology. So
You
I think
needed
that's
you
an
needed the
important.
computers were critical.
Yeah, yeah. So it wasn't that, you could have done it by an accidental discovery, but having to look at 1,000 stars was simply impossible in the
Yeah.
1960s and 70s.
Well,
And
it's a little more than that because I've glossed over this point, but the spectrum, when we spread the light out from the star from blue, green, yellow, and red, all the wavelengths, we actually spread it out into about 10,000 individual units of wavelength. And I have to give credit to Steve Vogt, who was at UC Santa Cruz, designed and built the spectrometer that we first used at Lick Observatory. So, without Steve Vogt building that spectrometer, we never would have
it's
had a chance.
a combination. Well, the being in the right place at the right time is a large part of science as well. But taking advantage of that moment is sometimes what makes one special.
Yep.
Um, Now, so suddenly there's a new technique, which is really neat because now you have two techniques, independent techniques for looking at planets. And I think the important thing is, again, a strange observation. It can be strange and usually wrong, but when you predict it, and it's exactly what you predict, it gives you a great deal more confidence that you're not
Yeah.
seeing something anomalous. Something I
Huge.
talk about in terms, by the way, in climate change, it's not just that the temperature of the Earth is rising. It's exactly what you'd predict from fundamental physics, and that gives you great confidence. But now two things. Suddenly, a Jupiter that's orbiting a star is observable. But really, what was interest to you when you first had that moment in the shower was not Jupiter's, but the question, well, maybe Jupiter's, because we know so little about life in the universe that who knows. But like the drunk coming out of the bar, you look where you lost your keys under the lamppost. The
Right.
simplest thing to look for is Earth-like planets, and that's what everyone. That's where the money is, and the interest is, and
Yeah. Right.
so take me through. So that new observational technique also led to the development of a new observatory, but also in principle allow you to I think to go to lower size, smaller size planets than you could just using Doppler shifts alone. Is that right?
Yeah. So there were two stages here. One was that the Swiss team, led by Michel Mayor and Didier
Mhm.
Queloz, um, improved their spectrometer. And I would say by around 2005, 2010, their spectrometer was producing superior Doppler shift measurements to what we could do. And that's just the truth of it. I can tell
Yeah,
you technically what they
yeah.
did, and it was brilliant. Um, but it was so good that they started finding Neptune sized planets and planets that were 5 times and 10 times the mass of the Earth. Okay, they weren't Earth sized quite,
Yeah.
but they weren't Jupiter's either. They were smaller and smaller
Mhm.
planets. And we were starting to find them too, but the Swiss team was doing a better job. And it gave us a hint. They wrote a couple of papers about this. It gave us a hint that there might be even smaller planets. And then the second big breakthrough, frankly, was the advent of two spaceborne telescopes, one by Europe called Corot, and then the really great one launched by NASA called Kepler.
Which Kepler was designed to look at something like 100,000 stars in a small
Exactly.
region of the galaxy, and to look at them every night to look for specifically this occlusion, this dimming, periodic dimming, and it was the first time that a systematic planet finding capability at a statistical level was possible, not just a random luck here or there, but where you could definitively look at large systems and begin to get the statistics of planets,
Yeah.
which of course, and like the statistics of many things, they're skewed, right? I remember I'd give public lectures and I show all the planets that were discovered, and you'd see a lot of Jupiter's nearby planets, and you'd say, well, maybe most planets are Jupiter's nearby their sun, but of course you
Right.
realize there's what called a selection effect. It's the looking under the lamppost. The easiest ones to find are Jupiter's nearby stars. And let's face it, in the Earth goes around the sun once a year. So even if you could measure that few centimeters per year or the occlusion of the Earth around the sun, you'd have
Right.
to measure many years. And so if a telescope is only up for 2 or 3 or 4 years, you're not going
Right.
to see systems that have periods of 10 or 20 years.
Right. Yeah. And it's worth pointing out that this spaceborne telescope called Kepler, funded by NASA, was led by one individual. And I only bring this up because it shows again the struggle of science. He wrote multiple proposals. His name is Bill Barucki at NASA Ames Research Center. He wrote multiple proposals to NASA stating that a spaceborne telescope would be able to watch the brightness of stars, indeed 100,000 stars, and measure the brightness so precisely that even a tiny Earth-sized planet crossing in front of the star would dim the star by a measurable amount. And what is amusing and of course telltale is that despite several proposals being turned down, Bill Barucki continued to write proposals to NASA headquarters, and eventually they said yes. And that led to the Kepler mission and the discovery of now about 4,000 planets, most of which are about the size of the Earth.
Yeah, no, it's an amazing see again a sea shift, and it is of course caused a great deal of excitement
Yeah,
because you say we now know that Earth-like planets are not rare, and in
right.
fact, you with Kepler, you and a student I think wrote a key paper
Yeah,
which won a big prize because you were am I wrong or the first people
yeah.
to kind of estimate the likelihood of finding Earth-like planets?
Yeah, there were several groups chipping away, but really the key one was by Eric Pettigura, who's a brilliant astronomer now. He was my PhD student, and now he's at UCLA as a professor. And Eric, the tour de force I can't even begin to describe, but it was an amazing tour de force. He simulated the errors, the systematic effects, the selection effects, the sensitivity to Earth-sized planets. All of that went in, and then he reanalyzed himself personally all of the data. I mean, we're
Wow.
talking about years, 4 years of data from the Kepler telescope,
Wow.
and found all the planets himself with his own code. And then we published a paper with Andrew Howard and myself. And Eric, of course, was first author and, as you say, received a prize for determining what fraction of stars in the night sky have Earth sized planets in Earth like orbits so that those planets would be lukewarm, allowing water to be in liquid form.
The first, basically, the first I mean, people had estimated. It's easy to make an estimate, especially if you don't have any data. And
Yeah.
but so people had speculated about Earth-like planets and how unique we are and all that. But this was the first time one had data to actually make a statistical analysis that gave you uncertainties and
Yes.
estimates that told you, hey, habitable
Yeah.
planets might not be rare. And by habitable, all we mean, or all that is traditionally means, is hey, there's water and a and gravity that isn't too large, the combination of the two, and 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 that
Yeah.
estimate that you guys made, in some sense, laid the basis for much of the excitement that is now what is called the field of astrobiology,
Well,
which
and it's worth recapping that Uh, first of all, our Milky Way galaxy in which we live has about 200 billion stars, and our universe as a whole has hundreds of billions of galaxies, each one of which is roughly like our Milky Way. And what we learned was that something like 10 to 20% of those stars have Earth sized planets in habitable like orbits. And so if you do the math, 10% of 200 billion stars, you quickly see that there's something like tens of billions of lukewarm Earth sized planets out there.
which
And
is
by the way, one last news note, we still have never confirmed that there's actually water on those planets.
yeah,
So there's probably water because let's be fair, hydrogen atoms and oxygen atoms are among the most common atoms in the universe. They're going to combine to make H2O. Nonetheless, it would be nice to confirm, has not yet been done, that there are standing lakes and oceans on these so called Earth like planets.
I think you again you lead me to where I was going to go in this regard, which is great. Because I'm going to make a statement which is going to cause some people to be to be concerned. Uh, I read astrobiology is a field which has, one could say, more hype and less substance than many other fields, and by that I don't mean to want to put down the people who are working in it. What I mean is we read about habitable planets and discoveries of potential life. We do, when people talk about the level of our knowledge is so little that to make the claims that are made that are often attributed to astrobiology is, I understand the enthusiasm, but it's not supported by the science. And while there's a great deal of money and attention that's being framed there, one of the examples I just give is, hey, the Earth is an Earth-like planet, but for some period of its history, it was frozen solid. It all
Right.
depends upon the distribution of continents around the Earth, as well as a few other things. So when the Earth's continents were right, so the albedo of the Earth was such, well, the Earth froze over. And so when people talk about habitable planets and Earth-like planets where we don't even know that there's water, but even if there is, we don't know if the continents are such that 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 the planet actually has liquid water. There are huge leaps of the imagination, and then claims about, well, maybe life has occurred here or there or there or there, because in extreme environments maybe it's here or there, when we don't yet know the origin of life on Earth, is a
Yeah, and
huge leap. And I
there's
think
a
it's really
huge leap.
important for people to realize that. I just want to moderate. But that hype should be taken with many grains of salt.
And there's a specific example of what you're talking about. I'll mention our Earth has some amount of water. Much of it is locked into the mantle of the interior of the Earth. We know that there are many oceans worth of water locked into the mantle in hydrated minerals. So you might ask, why do we have oceans on the Earth? Well, the answer is we have so much water associated with the Earth that not only does the mantle have water, but some of it leaks up to the surface and puddles into oceans and lakes. Well, that's great. But what if the Earth had had a little bit more water? Well, then thered be so much water, the whole thing would be covered. Look, the continents are only, some tens of thousands of feet high. Mount Everest,
Mhm.
20,000 feet high or so. It wouldn't take very much water to cover the Earth. So the Earth could either have been formed with too little water, in which case it would all be in the mantle, soaked into the sponge of the interior of the Earth, or the Earth could have been made with too much water. And somehow we're lucky to have continents and oceans. And let's be clear, if the Earth only had an ocean covering it and no continents, it would be difficult to build rockets, computers, electronics. You couldn't even build a violin in
Yeah.
water and have it
Yeah.
work.
Yeah, no, exactly. You could have intelligent dolphins, but
Yes,
unless they're a product of a hyper intelligent civilization and they leave the Earth and say thanks for all the fish, um,
right.
yeah, no, it's really important to realize that 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 a water planet, while everyone loves the idea of water, a water planet will not produce, if you're interested in intelligent life, as opposed to microbial life or
Right.
even animals which could exist in water. Um,
And the
the,
right
the
way
the
to
Earth,
say this, the right way to say this is technological life.
yeah,
Because
yeah,
as you point out, marine mammals could in fact be even more intelligent, certainly socially more
yeah,
intelligent than we humans. But technology, building mechanical devices, electrical devices, computing devices, never mind telescopes and rocket ships, really requires dry land.
yeah, absolutely, and yeah, it's true. Octopuses or octopi, I guess is the word,
Hmm.
are very
Right.
intelligent, as are dolphins. But there's another factor too. I mean, one could write science fiction stories about this, and that's the point. I think people should realize a lot of what is claimed to be science right now is science fiction in this area. It's incredibly important because of their new techniques that we're developing to
Yeah.
to be on the threshold of discovering the possible existence of life elsewhere, any kind
Right.
of life elsewhere, which is a great discovery. But take the claims with a grain of salt. But another thing that's relevant, and as I say, if you were going to write a science fiction story about about intelligent animals, or at least some kind of social intelligence in the ocean, is if you've ever been scuba diving, you can't see out there very much. And
Right.
so they're not so, it's not so obvious that they're aware that there's a universe outside that ocean, because of the refraction of light. And
Right.
so, there are many things. So, but again, even if you had continents, you have to have them in the right distribution to have water. And you
Yep.
also have to have a stuff to have a star that's quiescent and lots of other things. For
Oh
example,
yeah.
many of the
Oh yeah.
habitable planets are
Yep.
around they're discovered because they're close to their stars, and they can only be close to their stars and habitable because the stars are much less massive than our sun, and therefore you can be much closer without the water boiling off. But if you're much closer, you're subject to other aspects of your stars, if there's a flare or some other things
Right.
that could kill off life. So
Yep.
this the the there's a lot of work in what's called astrobiology about habitable planets that I think people, it's incredibly exciting, the techniques that we're developing, but people have to be wary of what they read, as they
And
always have to be.
even the rare Earth hypothesis, as it's sometimes
Yeah.
called,
Hmm.
includes some obscure aspects like our moon, which
Yeah.
orbiting the Earth stabilizes the spin axis
Yeah.
against precession. So, how many Earth-like planets in an Earth-like orbit do not have a fairly massive moon close enough to stabilize the spin
Mm.
axis of that Earth-like planet? You start adding all these factors, or I should say multiplying these factors together, and you start worrying that the number of truly habitable planets for long enough for Darwinian evolution to do its thing and produce technological life, it might be that the galaxy is filled with a few dozen of these or a few thousands of these, but not billions.
Yeah, I think the point is, my attitude has always been, I'm pretty convinced by these factors that intelligent life is extremely rare, but with 200 billion solar systems, rare can still produce a lot of stuff, and that's the wonderful
There,
thing about science. And
there are
but
lots. Yeah, go ahead.
well, it goes back. You probably know Frank Drake yourself. I knew him, and as
Sure.
well, and lovely guy. But people seem to think that there's a lot of content. The Drake equation is a Drake equation, isn't an equation. It's just a parameterization of our ignorance, and
Right.
saying, let's guess how many intelligent civilizations there are, and you multiply a whole bunch of probabilities, each of which you know almost nothing about, and you can come
Right.
up anywhere from one or zero to a billion. And I think the point I'm trying to say is, it's a field. Remember how I said with just one star, of course, and one planet, a lot of possibilities are. You need to discover a lot more things. We're in a field we have zero. We have yet to know anything experimentally
Right.
about these planets. And therefore, we have zero empirical data. And therefore, any claim of about the likelihood or not likelihood of habitable life, or where it's likely to form, is just pure hypothesis right now. And it's a field with lots of, obviously there's lots of ideas, and I've thought about them, and so have others, and you have, and there's lots of new techniques, but right now there's no data, and with no data, um, you, probably it deserves a little less hype, except for, every time we discover the discovery of new planets, which you pioneered, has been the data that's driving at least the next generation of experiments, which may allow us to get some signals for life. And maybe we should talk about then what's next, because I know you pioneered, worrying about the terrestrial planet finder. Oh, before I get there, something else I didn't know about you, that you're a poet. I did not know that. And I heard something about when Kepler died, or something like when that satellite died, that you wrote a poem, which I'm not going to read, but I did find it.
Yeah.
Um, and so,
I'm
do you
not
often
I'm
write
not a
poetry?
poet. I took a very well-known poem and recast it for our beloved Kepler that had died. And what was interesting, uh, it really did bring tears to my eyes and others, because Kepler was, I think, one of the most profound experiments that humanity's ever done. And interestingly, NASA's engineers brought Kepler back to life. They
Hmm.
actually figured out a way to use solar radiation and the pressure to reorient Kepler and overcome its hobbled state. So,
Amazing.
the poem was was premature, shall we
Okay,
say.
that's all right. Well, the poem can never be premature. It can just reflect the the feelings of the moment, and
Um,
um and
I,
and, and
I'd like to go back, if you wouldn't mind, to something just to touch
sure.
up your astrobiology rant there.
Okay,
Um,
sorry. I better me than you. Better I get the hate mail. Anyway,
exactly. Well, let's look at the positive side here. Um, NASA and ESA are planning missions to Mars, to the giant moons of Jupiter, to Titan, the large moon around Saturn, and also Enceladus. Now,
hmm
these moons are easily explored robotically.
yeah,
You can send a mission up for something like $3 per American. And that means you can go and sample the water that we know is there on all of those bodies I just
sure,
mentioned, and look for bacteria. So, in terms of the pessimism that you very rightly articulated, there is an experimental solution within our lifetimes, which is to send probes, examine the water literally for microbial life. And look, in 30 or 40 years, we will have visited all of the objects I just
mm
mentioned: Mars, Jupiter's
hmm
moons, Saturn's
yeah.
moons, a few others. And frankly, we're going to know whether or not the origin of life happened on any of them.
Okay,
That'll be cool.
yeah,
That's
no, yeah, of course. In fact, I'm a big supporter. I think you misinterpreted. I'm not pessimistic. I'm optimistic. I'm optimistic because every time you know nothing, there's a lot to be learned.
yeah,
So I guess my point to is just to point out how little we know, but that to me
yeah,
makes it exciting. I just
right,
want to point. I'm opposed to hype, but I love the fact that there's a tremendous amount to be learned, and we have the technology, not just
right,
in our solar system, but elsewhere. And I want to get to the elsewhere. But you're
yeah,
absolutely right. There's no doubt that that exploring, especially the Enceladus and systems, not so much Mars, it seems to me, which of course would be fascinating to find evidence for fossilized life or extant life or extinct life. But there, we the problem with that system is we know that it's been, that it's been in communication with the Earth.
right,
I'd like to see in the oceans of Enceladus, which in
yes.
principle has been separated. And by the way, if you asked me to bet, I would bet you now dollars to donuts that there's microbes there, and I bet you it's an independent genesis of life. I think life, as far as I can see, if the Earth is any example, evolves about as soon as the laws of chemistry and physics allow it to. But um, but that would be a profound discovery, and I can't wait for it.
Profound.
And
That would
it's
be
going to. And
profound.
by the way, it's going to be done not by astronauts. It's not going to be done,
Right.
even by Elon Musk or any of the people that get all the press. It's going to be done by robots because, and that's the other thing. I get a lot of, I've had fun debates with my friend Neil deGrasse Tyson about this, but the best science that NASA does is done without astronauts because astronauts, although it's exciting and adventurous, most of the money that's spent is spent on keeping them alive. Whereas, if and robots can go to places that astronauts just can't. So it's going to the most exciting work is going to be done there in our solar system, not by astronauts, I would argue, although it'd be wonderful adventures. But the
Yeah.
science, but then outside our solar system, it's definitely not going to be done by astronauts. It's going to be done by new technologies. And I know that you were one of the early people to be really pushing for the next step beyond Kepler because look, to make it clear, yeah, you can now see planets going in front of stars, but when you can see planets going around in front of stars, if those planets have atmospheres, then the starlight goes through those atmospheres, and in principle, you could look
Right.
for telltale signs of life. So maybe you want to go into what's next.
Well, there's a very exciting future right at our doorstep to watch nearby stars for the moment when a planet goes in front, as you said, and you watch the starlight pass through the atmosphere of that planet on its way to the Earth. And of course, when the light passes through the atmosphere of the planet, some of the light will be absorbed by whatever molecules happen to be in that atmosphere. And some of those molecules might be telltale signs of biological processes. The interpretation will be difficult, but the first step is almost at hand with the launch of the James Webb Space Telescope. And there will be others in the future designed specifically to measure the starlight passing through planet atmospheres. So there will be a great new field of sort of planetary atmosphere spectroscopy, allowing us to do chemical and you might say biological assays of the composition of those planets. So it'll be
Eventually,
exciting.
yeah, and eventually we'll learn a lot. I mean, the point is we have a sample of one right now, the Earth. So
Yeah,
we have an idea of what biological signatures you'd have if you were looking at the Earth from far away, but we don't know if those are generic, and we may
right.
be surprised. But for example, when I in my young days, when I wrote a book called Adam, and I probably might have even mentioned there, I would have thought that observation of oxygen in the free oxygen in the atmosphere of a planet would be a sign of life, because on Earth there wasn't free oxygen. All the free oxygen on Earth was created by life on Earth. But then I learned to be by people who know these things better than me. Yeah, that's true, but it's not the only way to get free oxygen. And so
Right.
you got to be careful. Anytime you see these things, you've got to be careful, and you'll need a lot of data. And we'll learn things. And what we may learn is that the biological signatures are something else, or maybe the best biological signature will be pollution. We don't know, it'll. We are in yet another golden era, and that's why I'm optimistic, not pessimistic, because we will have the tools in our lifetime to not just explore our solar system, but to image at least the atmospheres in one way or another, with spectroscopy, if not
Yeah.
visually. And who
Yeah.
knows, maybe even with new technological optical systems to actually image some
Right.
aspects of those systems. In the next 30 or 40 years, lots of things are possible. And so I know that you've been
Right.
spearheading that. And
And
but
it's not.
I think
I should
the
say
inform
it's not me spearheading it. I mean, there are people out there who are
yeah.
the real experts, and
What
so
I meant early, an
I,
early
I'm
proponent.
I'm cheering them on. Let's put it
Yeah,
that
but
way.
at a stage when you had a lot of imp of play
Yeah,
of influence because of the work you've
yeah,
done on planets, you're one of the first people to say, "Hey, we've got to keep going. We can't
yeah,
stop with Kepler," and that's very
yeah.
important for significant scientists to provide that kind of
Right,
rallying cry. But nevertheless, I think it's really important to point out that the importance of having made the discoveries that you and Michel Mayor and his collaborators have done, and I think it's we want to point out that that you and Michel happily shared the Shaw Prize for the work you did, and I think and of course and Michel and Didier went on to win the Nobel Prize, and many of us thought that you. I still think that it would have been a nice thing for you to be a part of it, and then these prizes are arbitrary, but the significance of it, I think, in the long run, is what's important. And as Feynman said, that's much important. The discovery is much more important than,
right.
I'm just in it. I hope every day you feel a sense of awe and wonder at what you were able to have been able to accomplish thus far.
And,
But now I want to end by going the next stage. You're not satisfied in
yeah,
just because you're what got you interested in that shower wasn't just discovering Earth-like planets. That was the
right,
technology. But what you really wanted to know is the other technological civilizations. And that's
right.
been a question. That's a central question. Are we alone as an intelligent society
Yeah,
in the universe? And of course, much as have written recently, and people hate the fact that the way if we're going to discover that, it's not by going around with spacecraft or expecting them to be coming here and doing neat things. So I've argued that what we see as UAPs are definitely not aliens, much to some people's chagrin. The way to do it is to listen or look. And you've been involved for a long time
yeah.
now in what we call SETI, and what we call SETI, or you can call SETI, the Search for Extraterrestrial Intelligence, and that's developed a lot too. So that's occupied the most recent phase of your career, and I wanted to spend a little while talking about that too. So,
Well, I'm very appreciative of several dozen astronomers around the world who are using radio telescopes to listen, if you will, to use that term generically,
mhm.
listen for radio waves from advanced civilizations. There's a wonderful group called Breakthrough Listen that has a whole team funded by Yuri Milner, and they're working very hard to use the world's largest radio telescopes to detect signals, radio wave signals from other civilizations. It's a very reasonable thing to do, and it's the best, maybe the best we can do. There are other ways to detect
Let me
technological.
let
Yeah,
me stop there for a second, because I know you're looking at the other technologies, and I want to discuss them. Radios get the most play in the
yeah,
media, and again, in my book about Star Trek from 1993, I spent a lot of time
yeah.
the early stages of SETI with talking about, but trying to moderate enthusiasm by pointing out that how hard it is, that even if intelligent civilizations are out there, the universe is a pretty big place, and so is the galaxy. And it's not only, and as I like to say, now I have guides, but I used to say when I got cable TV, I immediately gave up watching TV because suddenly I couldn't find what I wanted to find anyway. There were so many
Right.
channels, and that
Too
was
many
just with 200
frequencies.
channels. But in the
Right,
universe, you have an infinite number of frequencies, and
right,
and
right.
one can give arguments for why it's really, really tough. So that even if intelligent
Yeah,
civilizations are out there, you shouldn't expect the absence of hearing anything to be, absence of evidence, as Sagan once said, is not evidence
right.
of absence, and that's a clear example. It's a
It
really
is.
tough business, and my own bet is that even if intelligent civilizations exist, I'd still give small odds that we'll know about it. But what you've been, so radio is one way to look for it, and there's been a lot
That's
of
right.
work, and listening for I Love Lucy from or whatever from the distant galaxy or distant stars is one way. But you've been looking at other techniques, which I find fascinating. So since they don't get a lot of play, I want to talk about them.
Well, as you pointed out, the radio waves are just one part of the so called electromagnetic spectrum, which includes infrared, optical visible light, ultraviolet light, X rays, gamma rays. And frankly, any of those are reasonable parts of the spectrum of light that advanced civilizations may use. And I can even argue that it's the higher frequencies like optical and in ultraviolet and X rays that have some advantages in terms of keeping privacy, uh, being able to send individual photons on or off that give you bits like ones and zeros on a computer. But in any case, what I've been involved with is searching visible light, the light that your human eye is sensitive to, for laser beams. Because some people have pointed out that our galaxy, our Milky Way galaxy, may have a galactic internet, and you can't string Ethernet cables between the stars or from a star to a spacecraft or a spacecraft to a colony and so on. Instead of fiber, you would use laser beams. And so we might be able to eavesdrop on the galactic internet by catching one of those beams as it travels from a colony to a spacecraft, and the Earth happens to be in between. So my group has been using telescopes, visible light telescopes, to look at different stars, different parts of the galaxy, even within our solar system, for laser beams. And we
And
haven't found any.
yeah, but again, not finding it is not in evidence. But one thing that I think is interesting, and a recent development that you've been involved in, which is a little complicated, but not too complicated, is the fact that, yeah, if it's laser beam, you have to be able to detect the signal, and it has to be in your direction. But things like the sun are natural lenses, or what are called
Right,
gravitational lenses,
right,
which is an area that fascinates me, and I've worked on as a theorist. But the fact is that because gravity bends light, objects
right.
like the sun can magnify other objects behind them. And as you pointed out in at least a recent publication, I think you can imagine the sun acting as a gravitational lens. So in one of your searches, I think you once talked about not having seen a signal that might come from kilowatt lasers or something like that.
Right,
But if you happen to use the sun as a magnifier, you could detect a 100-watt laser on a
right.
star. How far away? How far away?
Well, the nearest star is Alpha Centauri and
Mhm.
Proxima Centauri. And yeah, if you use the sun as a gravitational lens, the light from those stars can be lensed by the sun very close within our solar system. And so we're pointing our telescopes at those focal points, hoping that some advanced civilization has put its probes there using the sun as a gravitational lens, and maybe we can eavesdrop on the communication that the probe is involved in.
Yeah, it's a long shot, but why not? I think it's amazing to use these.
It's a long
Again, it's
shot.
a new technology, and you never know what you're going to see unless you listen or look. And if it doesn't break the bank, Why not?
Right.
Look, that was always my attitude about SETI. If it doesn't break the bank, it's a long shot. I wouldn't bet on it, but why not? And if it's a billionaire that funds it, even better. Um,
Yeah.
and so I just find that this romantic search, which has really been going on for much of your career, that's driven you and for which you've made major discoveries and pushed things forward, to be a lovely example of the quest, that the inexhaustible curiosity of humans, and what you can do if you keep trying. And I hope what our discussion has also showed is something, not just the incredible humility, which I know is not false humility in your case, but the generosity of spirit towards your colleagues, which I hope has come across, because it's what I've come to know from beginning to know you as an individual and as a friend. That generosity of spirit is so pleasing, and it's one of the things that in my mind makes you such a, not just such a wonderful scientist, but such a wonderful human being, and I hope that's come across here. So
Well, that's awfully generous of you. All I can say is we should all feel lucky. I think we should feel lucky. We live in this era when we can ask these questions and make use of the resources here on the earth to try to answer these questions. It's amazing that, it was only a 500,000 years ago that we were clambering out of the East African savanna, and here we are now with spaceborne telescopes trying to answer questions, ironically, about the origins of other technological beings, which in effect is an effort to answer a question about our own roots. Where did we come from? And we may get the answer, ironically, by looking to the stars.
yeah, in fact, that's a wonderfully poetic way to put this, because this is an Origins Project Foundation podcast, and it is, to me, remarkable that, and it not, maybe not that remarkable, that the way we may learn about our own origins, which is really what it comes down to. Where did we come from? How did we get here? Will come from looking at the heavens and not at the earth. And why? Because we're one example, and it's really hard to know.
Right.
Although I actually think we're coming very close to discovering the chemical processes that may have led to the development of self-replicating living systems. I actually think that's an area where there's been a lot of developments, and I've been following it, and we'll talk about it in this podcast. But surely, by looking out and seeing what the universe has to offer, if life is ubiquitous, then we'll learn a lot more by seeing lots of kinds of life, about the kind of variety of life, whether there's a unique chemistry of life. We'll learn a lot more about ourselves by looking up there, and I think that's one of the reasons to continue to look out there. When people say, why should we fund these things, we should be thinking about ourselves on Earth. If we want to understand ourselves and our place in the universe, well, we have to look out at the universe and see it. And it's nice to have people like you who've been looking out at the universe and with their tools going boldly where no one has gone before. So thanks, Geoff, for and for all you've done, and for the wonderful discussions here, and again, your ability to, and your interest and enthusiasm to explain this to people. It's been a pleasure to talk to you.
Thank you, Lawrence, for your very generous interview. This has been a wonderful time.
Thanks. I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century, and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.